So welcome everyone to the second of 3 conversations with notable scientists here at Berkeley Lab. My name is Jeff Miller. I'm Head of Public Affairs and your host for today. I'm also your voice as we converse with my guest as we navigate the world of supercomputing. My guest's name is Kathy Yelick. She's the Associate Lab Director of Computing Sciences. Please give her a very warm welcome.
Thank you.
Obviously, your fans are in the audience. I'm sort of the stand-in, the non-expert guy, so I'm going to ask the very most basic question: what is supercomputing, and what is its value to society? Begin at the beginning.
Supercomputing is a term that we use to talk about the biggest computers, or really it's the fastest computers, regardless of how large they are. So the computers that are used to solve some of the biggest computational challenges in the world. And those are used for things like basic science problems, understanding the universe, understanding the world around us, climate change, for developing new materials, new chemicals, and new solutions to various problems in the world.
So let's give the folks a sense of scale here. Are we talking about, 1 million laptops lashed together? I mean, what's the processing power here?
Well, the fastest computer that we have here at Lawrence Berkeley Lab is in the NERSC facility, and that has 150,000 processor cores. So you might think of it as about the same as 150,000 processors of laptops.
So 150,000 laptops.
Yeah. Although
together?
some of your laptops might have a couple of processors in them today, 2 or 4 processors, but yeah.
And could you explain what NERSC is for those who might not know?
So NERSC is the National Energy Research Scientific Computing Center. It's a supercomputing center, so it's a center for that runs supercomputers for the Department of Energy's Office of Science. So we run supercomputers and also have data storage systems and services, expert consultants to help people use these systems. And we have about 4,500 users today all over the world, out in universities and in other labs, and they're all working on basic science problems of interest to the Department of Energy.
Okay. So revolutionary is a word that we hear a lot, but I think in the case of supercomputing, it's probably a fair thing to say that supercomputing has revolutionized science, and then the second part of that question, changed our lives. So let's talk about the science part first. What has the impact been on science?
Well, if you think about the basic science process that you learn when you're in middle school or high school, you learn about experiments and theory. So, the first experiments you might do in one of those classes would be to roll a car down a plane and down some kind of an incline, and then measure the amount of time it takes, measure acceleration, and then try to show that force is equal to mass times acceleration. So that would be a theory, a very simple theory, but one that's very powerful and is used a lot today to explain things. So F equals ma, and then the experiment is this process of measuring the acceleration of this. Say a little car or something going down an incline. And now that's a fairly simple theory that you can write down, and you can measure these things, and you can plug them into the formula and see whether or not it matches your theoretical understanding. As we get much more complicated the systems that we're trying to understand. So understanding something like climate, why is it changing, or how is it changing, and how will it change depending on what we do with various things, then you have a much more complicated theory that goes along with it. And you can no longer just write a simple formula and plug in, take a few experimental numbers and plug them in and see whether or not your theory is correct, or that that they match your experiments. And so instead what you do is the process of modeling and simulation, which is when you've got a very complicated theory. It might be pages of equations, and you then implement a program, a piece of software that implements those equations, and that is the theoretical side, and then you can run this program and see whether or not what that theory predicts. And then you can try to go back also and measure it against some experiments. And so you use computers.
Let me ask a really basic question. So you have a formula that you're proposing for a problem. So how does that actually get translated into a form that a computer can actually read or use?
Well, so you have some scientists who have to understand both the theory, that is the equations, and also have to understand how computers are programmed. And they will write down something that says, so for example, with force equals mass times acceleration, you can write a little program that says, calculate the force by multiplying these two numbers together, and you could have a program that reads in a whole series of numbers and then calculates the force. Obviously, that's not a particularly interesting example. You could do that with an Excel spreadsheet, a very simple programming kind of model, but if it's a very complicated formula, you just have a much more complicated program that will go through and calculate various numbers based on their inputs.
So it seems that there are teams of specialists here that have to be involved in this type of work, correct?
You know, one of the interesting things about this area, which we call computational science, so it is applying computers to science, is that it's highly interdisciplinary. And so we are using computers to understand physics, to understand chemistry, to understand biology, understand various engineering problems in energy and other things. You need to have an expert in the science. You need to have an expert in the computers. Often, especially today, with these supercomputers can be very complicated to program. You need to understand something about how to map those programs onto those supercomputers, and you often need in the middle of it all a mathematician who really understands the equations and how to translate them. So you have these interdisciplinary teams that have to work together, and it is both one of the most, I think, challenging things about computational science, and one of the very exciting things about it is if you go into a new area, you'll get into a room with people and you can barely even communicate with them because they may all be speaking English, but some of them are speaking in equations, some of them are speaking in code. They want to write down little pieces of code. Some of them are going to talk about computer architecture, and the goal is to, and some of them are going to be mathematicians who want to prove theorems. And you have to get all of these people to be able to talk to each other, somehow translate between the different languages in order to solve the problem.
So who does the translation?
Well, a lot of times it's the mathematicians and the computer scientists in between the hardware and the science domain. But it takes some work on both sides. So it's not as though you can just hire a translator and automatically convert from the science to the computer code.
Okay. Talking about now the effect of supercomputers or computers in general as they revolutionize society. From your perspective, what would be some of the most obvious examples, and maybe some that we haven't thought of?
Well, some of the most obvious examples, of course, are things like iPhones, Siri. I think 40% of people actually apparently look at their iPhone before they even get out of bed in the morning. So, I mean, this has changed the way we behave, right? And I think Google search has also quite obviously changed. It changes the scientific process, but it changes the way non-scientists work in society. I mean, how many times a day do you go to Google and say, whether you want to map something or you just want to look up some terminology or you want to look up, find some product online or whatever, it really has changed the way we live.
So I know you recently spoke to students at UC Berkeley about how computing can change the world or save the world, perhaps.
That's right. I think.
And what did you tell them?
Well, what I talk to students about, because I think computers, you can get kind of wrapped up in just how computers work, how fast they are, and that's part of what computer science is all about. How do you build computers and how you program them and the software tools around them. But a lot of, the reason we have these computers is because they can be used to solve really interesting and important problems. And I really talk about two basic classes of problems that computers can be used to help with. One of them is really understanding the world around us, and it is related to things like understanding climate change, but also then developing alternative fuels, developing more energy efficient devices. So these are running simulations, so simulating these things to try to figure out what is the best way. LEDs are used in lighting, energy efficient lighting materials, things like that. Those are all examples of things where computers have been used to help develop solutions and also to understand how things are changing. All the way back to the origins of the universe, we use computers for those things. And the second kind of major real problem, and I think people appreciate, is that computers can help us with human health. And computers are certainly used in designing drugs. They're used in designing artificial devices, prosthetic devices. They can be used for analyzing data around us in terms of understanding the behavior of disease and the spread of disease and things like that. I worked years ago on a problem which was simulating blood flow in the heart, and that that kind of a simulation, you're trying to understand the fluid dynamics of the heart, and it can be used to do things like design artificial heart valves, and used to develop treatments for infants who are born with a particular kind of congenital heart defect. So it's got real applications, and there are many different areas in which it comes up in human health.
So I'm sure you've seen changes in the students you've talked to over the years. So when you talk to them about that, is there just nodding and there's just assumed that that's the case, that these are world-changing opportunities for them? Or is there any convincing that you have to do?
I think that computers still there's in computer science there's still sort of a reputation that it's all about going into your office or into your home and just sort of typing on a computer for hours at a time, and certainly that kind of problem solving in computers is an important part of what you do as a software developer, as a computer scientist. But the fact that there are these applications of computers and understanding how they're used in science, I think, is not something that's so well understood by the students coming in. And so that's what I feel I have to explain to them, is that it's not just about the computers themselves, it's about the amazing things you can do with them.
So do they understand, or other folks, and for that matter, who you come in contact with, really understand the role of a national lab in this process? So you mentioned NERSC, and that's a user facility, and we should talk a little bit about that, about how it's public and accessible to scientists from around the world. So we can start there, but also in thinking about this, a national lab, assemblies of interdisciplinary teams of scientists looking to solve big problems, is that something that's really distinctive about national labs, but about this one in particular?
I think that Berkeley Lab is really unique in offering both access to unique facilities of various types of facilities, including the supercomputing facilities. So these are kinds of supercomputers that cost tens of millions of dollars. It's not the kind of thing that even a university will typically go out and buy. And also the expertise. So there's all this expertise within the lab about how to design algorithms for these supercomputers, how to program them, and how to develop the applications for all of these exciting disciplines. And so I think that the labs in general play a unique role within the research landscape, in that they really offer these unique facilities for some of these big science problems. So science problems that an individual scientist can't do at home or in their own lab with their own lab notebook or just their own personal computer. It's really there are some problems, and not all science problems, but there are certainly some problems that require big facilities in order to to address that science problem. And facilities like NERSC are an example of that here at Berkeley Lab.
So earlier you mentioned, when you're speaking with students, climate change and climate modeling. So let's spend just a little bit of time talking about probing a little deeper in some of these examples with huge societal impact. So climate modeling visualizations would be one example, and then let's talk about human health as well. But let's start with the climate again.
Well, if you look at something like climate change, it's a very complicated set of physical phenomena that you're trying to capture, and so you're building a model to try to explain what happens if we if we decrease the amount of carbon that is being produced every year. What will happen to the climate? Will the oceans, will the oceans still rise? Will the level still rise? Will the ice sheets melt? I mean, there are a number of questions that you can and do answer using these computer models and simulations of something like climate change. We're also developing things like solutions, understanding the combustion process, which is used in so many of our transportation and in big power plants and things like that, and trying to optimize the kinds of devices that we build to make them more energy efficient and produce less emissions. And so those are the kinds of things that you can do with computer systems. And both of those are examples of some of the biggest simulations. They have large interdisciplinary teams of people that develop the codes and run them and sometimes it's different people who run the codes from the ones who are analyzing the data. So there's large teams involved in these projects.
So from the public perspective, the product would be something that they could see on a computer screen. In the case of visualizations.
In the case of visualization, it may be, in climate change, it may be something like a map, two maps that show, with and without some change in policy, or with and without some change in the way, cars are designed or something in terms of the amount of carbon that's being produced. So there can be, you can see sort of a before and after, or a with and without phenomenon. But it's also actually in the basic science behind the products that they might be able to buy. So being able to buy a more energy efficient car, or a more more energy efficient lighting, or other things like that. So they're basic science problems that really turn into new devices for people to buy.
How about with something like neurodegenerative diseases?
Because Berkeley Lab and the NERSC facility are really focused on basic science problems within the Department of Energy, there are basic problems that are applicable to both health and also applicable to energy. So one example I like to use is a project by Valerie Daggett at the University of Washington. She does massive numbers of simulations. So she was looking at proteins and trying to understand how proteins fold. And so they run simulations to look at the dynamics of how proteins fold. This field is called dynamiomics, which is one of the more complicated.
Dynamiomics?
Dynamiomics, one of the more complicated.
Can you spell that for me?
No, thank you. And but what she did in her group was to run 10,000 of these protein unfolding simulations to see exactly what the dynamics are of these proteins, and then store them. So think of it as like a movie catalog now of this large set of proteins, and they've been used to understand some of the basics, properties behind disease-causing disease phenomena such as mad cow disease and Alzheimer's disease. So it's not as though they started out saying, well, let's look for a new drug to cure Alzheimer's, but they understand the basic mechanism of the proteins that will allow people to perhaps develop more targeted, more effective drugs for diseases like that. And so those are some of the kinds of problems that people use, and they take these and they store this database now of these movies, if you will, and let other scientists access this. So different scientists can look at that data set for different problems. And this is, I think, a really healthy change that I see happening in science and in computational science. Is not just one science group running the simulations and looking at the output, but a whole team of people, as I said, build them, but then they also make the data available to the scientific community. And an important part of the scientific process is having other scientists look at the data and see if they agree with it, but it also means that other scientists can look at it for completely different phenomena and make discoveries about that. And that's happened with this group of protein simulations. So
another benefit of having public science, having the results publicly accessible.
Absolutely. We have a set of what should I call them? Sort of like sophisticated web interfaces at NERSC that we call science gateways, and those are where some of these scientific data sets, large scientific data sets, are made available through a web interface. So we actually, the data is out there on the web, and that web interface is not necessarily designed for, average Americans go look at it, but it is available in many cases to them, and but they're designed for the scientists in that domain. So a scientist who's looking at designing new materials for batteries, or trying to understand something about neurodegenerative diseases, can look at this database of results.
I don't imagine the results happen overnight, so how much computer time are we talking about for some of these larger problems? Millions of hours, or what?
Well, so this year, NERSC will provide about 1 billion computer hours, a little over 1 billion hours of computer time to these scientific problems. And any one of them, the interesting thing is that basic scientific discoveries can happen all over the range. So there are projects that have used tens of millions of computer hours every year, and there are others that may only use a few thousand hours every year, and but they have access to these unique systems that are designed for scientific computations, and the expert services and the consultants. And some people have very large data sets, less computing. So we have all different combinations of users, but they're very large computations and very large data sets in many cases.
Okay, so let's switch gears for a second and let's talk about your personal computing story. So way back when, did you plan on, did you know that you were going to become the Associate Lab Director for Computing Sciences at Berkeley Lab? Was this something you planned on? Was there a mentoring moment?
No. In fact, my ambition when I graduated from high school was to become an astronaut. That was my plan, and I went to MIT, and so it seemed like a good place if you wanted to learn how to become an astronaut. And they said, well, some people said, well, you should take this programming class because everybody needs to know a little bit of programming. And the freshman year at MIT is pass-fail. So they said, take it pass-fail because programming is really hard, and a lot of people don't do so well in the class. So I took that class, and I said, that was really fun. Maybe I'll take one more of those classes, but then I was still going to be done with it. And so I took the second class, and by the end of my freshman year, I decided this was just so much fun. That was what I wanted to do, and that's how I got into it. And I really got into it not because of the maybe more because of the applications of computers that I've been talking about so far in terms of saving the world with computers. I got into it because I just loved the process of programming, and it's like solving a puzzle. I mean, whether you like crossword puzzles or other kinds of mechanical puzzles or anything, it's about it's that process of struggling to try to get something to work and then making it work, and then just realizing it's just very exciting to realize that you've gotten something to make something happen that wasn't obvious whether you were going to be able to solve the problem.
So let's dial back a little bit to the astronaut thing. So you were growing up in what home state?
I grew up mostly in South Dakota, so Sioux Falls, South Dakota was the
reaction. So in South Dakota, when you were growing up, was it widely known that you wanted to become an astronaut? Did people think that was a cool idea?
No, it was. I have to say, it wasn't so clear what I wanted to do in South Dakota, but I knew I liked math and science. That was probably the one thing I was pretty sure about. And but it was. Yeah, I got a good education in math and science and was able to go on with that.
So any career advice for those who aspire to follow you on a similar path?
Wow, I think one of the pieces of advice I got from a math teacher when I was in high school, and it's hard advice to take, which is just to recognize that when you are making decisions about what classes to take, you are closing doors along the way. When you decide not to take the next math class or the next science class, or for that matter, classes in other disciplines. So, to be very open-minded and continue exploring things. I mean, if anything, I wish I'd taken more math as an undergraduate because there are areas of science where I'm not that familiar with the mathematical foundation. So, just to stay very open to the different disciplines, and I think the other thing is that being put into a large freshman course as I was, and as our freshmen here are at Berkeley, with 300, 400, 500 students all learning how to program, it can feel pretty far removed from the exciting, great things you're going to do with computers. And we try to give students a feeling of that when they're in those classes, but you want to stick with it and sort of see if it's something you like to do. I think that's the other piece of basic advice I would give to people is find something you love to do. I consider myself incredibly fortunate to be able to do research at all, to be able to work on problems and fail at them, which is part of the scientific process, to be able to say, I have a hypothesis, I'm going to work on something, and that it's okay for that to not work out because you learn a lot about it. And not everybody gets to do that. It's pretty amazing.
So big challenges facing supercomputing. And am I reading this correctly? There's a supercomputing race to have the largest and fastest computer. Is that really going on, and should we really care about that?
Well, I think that what I really care about is how well we can continue to design computers that are better and faster and more effective for solving real science problems. And there are ways that we measure the speed of these computers, and so we can get into some competitions about that. But what's really important is if you look at something like an iPhone. So an iPhone 20 years ago would have been the supercomputer at NERSC was a Cray YMP. That is the capability of what's in your iPhone.
How many years ago was that? Just
about 20 years ago.
20 years
ago, yeah. So that would have been a one-ton, $10 million plus supercomputer, not your iPhone. And so that kind of scaling has certainly affected supercomputers, but they affect computers through all different scales. And what I'm very concerned about right now is that we're seeing real problems in the technology going forward. That is, can we make supercomputers any faster? And it's always hard to know, or computers in general any faster. It's hard to know what will get out of that in terms of either scientific instruments or in terms of personal devices, but we would not have Google or iPhones if we hadn't made computers faster. The problems that we're running into right now, probably the easiest one to understand is if you have a laptop and you put it on your lap for an hour wearing your shorts, you will often get kind of burns on your legs. They are very hot. And computers today are very hot. And that is the problem. And it used to be that the processor manufacturers could just make processors go faster and faster. There was a lot of engineering and research behind it, by the way. I don't want to dismiss that, but they were able to continue making processors go faster. But heat density has now become such a problem that they really can't make the processors any faster than they were. So instead, the manufacturers are putting more processors onto a chip. But we're very concerned in supercomputing about this issue of energy use, how much energy the computers use and how much energy is wasted in heat, what's a very efficient way to run our computing facility. And so there's a couple of things we're doing about that. One is we're building a new facility. It's going to be located here in Berkeley on the hillside. We're taking advantage of the fact that as I was in Washington, D.C. yesterday where it was 97 degrees or something like that. It's rarely 97 degrees in Berkeley, which means that we can, thankfully, exactly, we can use outside air cooling to cool our supercomputers. And that makes them much more, the facility much more energy efficient. And it's really, Berkeley may not be the only place where you can find cool, cool climate year-round, but it is really unique relative to where a lot of the other computing facilities are.
How about the explosion of data and just the need to sift through it and try to find information, let alone knowledge?
Right. I think that everybody who has a smartphone or any kind of a phone with a camera on it understands this data explosion problem because you get pretty high quality cameras and you can take pictures. You can take so many pictures that you can't find anything among those pictures, and that same phenomena is happening in science. So we can build scientific instruments like the Advanced Light Source or looking forward to a next generation light source that will have such high resolution, if you will, and such high repetition rates. So think of it as movies that are coming at you so fast that you can't, that you need a computer to analyze the data. You're not going to just look at the data with, with human beings. So we have these huge data sets that are coming from genome sequencers, that are coming from detectors, that are coming from particle detectors, light sources, and so on. And that is also changing science. And what it's doing is, as I described before, scientific theories we were implementing with these computer programs because the theories were very complicated. Well, now the data sets are so large and so complicated that we need computers to understand the data as well. And so there's this big, I think, revolution happening in computing applied to what's sometimes called big data. It's really about complicated data coming from all kinds of different sources, people finding information among, and data where it's not clearly labeled. So, the fact that, as all of you know, when you're searching the web, Google or Amazon or whoever knows what you want, perhaps even before you know that that's what you want to buy. Those ads are very well targeted because they are able to analyze this data. Well, that's in the commercial space, but in science, we would like to be able to do the same thing. We'd like to be able to discover things that are too complicated for a human being to just sift through the data. There was an example recently at NERSC of running a data analysis on climate data. This is data coming from climate simulations, and it was run on 80,000 processors, so across most of the largest machine that we have there, and could automatically detect what looks like a hurricane. Now, you may think that a hurricane is obvious if you're living through it, but if you're looking through several, tens of years of climate data, trying to figure out where are these events happening because you want to study those particular events is not, it's not obvious. And so there's huge, petabytes, terabytes, or petabytes of data that you may need to look through. And so you need computer programs to help you sift through that data.
Well, let's give us a visual example, a visual cue of what's happened. Could you just explain what we have here on the table?
Right. So this is this is some memory from the first supercomputer at Berkeley Lab. It was actually before Berkeley Lab was named Berkeley Lab, and this is from the CDC 6600. And this has They built computer systems a little bit differently at that time. So today, when we talk about a word of memory, it has 64 bits in it. Usually we'll talk about 64-bit words. That's 64 zeros and ones. So in this particular kind of memory had 60 bits. And this is 64 of those 60-bit words. So this is, pretty heavy for 64 words. So just think of that as,
Yeah, I wouldn't want that in my iPhone.
You don't want that in your iPhone. It wouldn't do you much good in your iPhone. And just, by comparison, this is about 500 million words of memory on this little thing here. Yeah. So, and this is the kind of memory chip that is in our supercomputers today. So 500 million and 64.
So what is exascale computing? Yet again, another...
Yeah. Exascale. So exascale computing, the word stands for the speed of the supercomputer. And exa is 10 to the 18th. So it's 10 to the 18th floating point operations per second. We call those flops. So just think of it as 10 to the 18th arithmetic operations per second. So you want to be, multiplies and adds. So we've got a 10 to the 18th. Now 10 to the 18th is a pretty big number and a little hard for us to kind of wrap our head around in general. But I like to think of it in terms of the computing capability of people. So let's just say in round numbers, there's a few billion people on the earth, and each of us, let's say that we can all add and subtract and multiply numbers at a rate of at one of those every few seconds. So we would say that we can do about 1 billion of these arithmetic operations per second on the earth. So we would call that a gigaflop. And but now that means all men, women, and children doing arithmetic 24/7 if we want to have a gigaflop.
That is not a possible scenario.
No, but just to give you an idea of what, and now an exaflop is 1 billion Earths. So it's 1 billion of those. So it's 1 billion Earths where everybody is computing 24/7. So that's how powerful an exaflop is, and that's what we're trying to build. Today we're at a mere petaflop at NERSC, and there's about 10 times that, and the fastest supercomputer in the world. So that's only 1 million Earths. So we're trying to get from 1 million Earths to 1 billion Earths.
So before we take the first question from the audience, are there any limits to this? Can we just keep adding more and more power, or when is it going to stop?
Well, as I said, one of the problems already is with the heat density, and so the answer is no, because the way we got to from this kind of memory and these kinds of, a 1-ton iPhone 20 years ago to an iPhone that you can carry around is by making the transistors, the basic little computing devices that are taking in ones and zeros and spitting out ones and zeros, and making them smaller and smaller. So, but we are also making those whole processors work faster. So the first limit that we're running into and have run into already is the heat in those processors. And the second one we will run into is once you get down to the atomic scale, we can't make the transistors any smaller. So these are all things that will happen in the next 10 to 15 years.
Okay, unless there's some hugely fundamental discovery that alters
That's right,
the course.
And which certainly we are working on alternative materials and looking at other kinds of computing devices and things like that.
We're sure this will happen at Berkeley Lab. Of course. Okay, let's take the first question from the audience.
So the question, I'll just repeat it, was about whether the supercomputers at NERSC are water-cooled or air-cooled. And in the supercomputers today, we do use, in the fastest one, we actually just turned off one that was air-cooled, and now we have one that is liquid-cooled. It's not cooled. It's not sprayed right on the cores, so it's not liquid cooling in the cores. And we can still use the climate here to cool the liquid outside using things called cooling towers. So, but our supercomputers are liquid cooled, and some of our other smaller computing systems or less powerful computing systems are air cooled. So we use a little bit of both.
So cooling is a factor for our computational research facility building that's being constructed here, is it not? And what was the solution? Did we not craft a...
So we have a really unique solution that that takes advantage of both the temperature in Berkeley and the hillside. There's a lower level where we don't have computers or people in the building, and that lower level brings in this outside air in order to cool the air-cooled part of the supercomputing facility. And so it's a really unique design. There's a kind of a metric of inefficiency of a computing center that people use called PUE, and typical computing centers might have might have 80% inefficiency. So every bit of power that you're bringing in to run your computer, there's another 80% on top of that you're using for cooling and loss in the power systems and things like that. We think that this computing center will have one of these PUEs of about 1.1, so only about 10% overhead. And we're now getting down to a small enough level that we just don't think, you can't go much lower than that.
All right, another question from the audience.
Hi. What is your favorite programming language?
My favorite programming language, well, to be honest, it's a language called Clue, which I think does not exist anymore, but it's very closely related, and a close second in terms of my favorite programming languages would be Java. I like both these languages because they have very powerful mechanisms for what we call abstraction in the programming language community. But what that really means is being able to have very complicated parts of the program that are wrapped up and kind of hidden behind an interface that can be very simple and elegant. And it's still, even as a software person, which is really what I consider myself both on the research side, and as I said, I love writing software from the time I first started that, it is still astonishing to me how complicated the programs are that are written today, whether we're talking about millions of lines of code in a climate model. So each one of these lines of code, if you think about it, a programmer on average writes about 10 good lines of code every day. So we've got millions of lines of software, and that's true also when you look at commercial applications. I mean, things like web services and things like that. They're very complicated programs, and the only reason that that's possible at all is because an individual programmer does not have to understand all of the complexity in the system. They understand the piece that they're working on, and the rest is hidden behind these abstractions.
So we hear the term citizen science a lot, and I think maybe in this sense it could be as individual machines at home become increasingly powerful. Is there any role for the citizen scientist in supercomputing that you can see?
Well, I think that there's certainly a role for citizen science in the data analysis area. This is one of the areas in which we're bringing in, by making these data sets available, it means that individual scientists all over can look at them and can make scientific discoveries even if they don't directly have access to the experimental device or the supercomputer, that they can look at the data and they may be able to analyze that at home using sort of a citizen science model. And this has been used. There's a process of looking for supernovae, so these exploding stars, and in images. And it's being done with a combination of mathematical algorithms that look at the images and learn from the images what is a supernova by having people mark them, and by having people look at them, looking at the images. So there are you can have these kinds of scientific problems that are examined by a wide range of people all over the place, including individuals at home.
So do you think the consumers have been spoiled by all of these developments, that their expectations that things are just there's going to be more and more and more always?
I think even scientists are a little bit spoiled about this. I think everyone assumes that computers will get faster and faster, even though they may not think they care, right? They may not think it matters because their iPhone is probably about as fast as they feel they need it, although Siri can sometimes go and think for a while when you ask it a hard question. But for the most part, people aren't worried about the fact that their computers they don't seem slow, because we use them for whatever we can do in a reasonable amount of time on the computer devices that we have. What we don't know is what scientific discoveries or personal inventions, home kind of devices for your home or for the office or whatever will not happen if we can't make computers that go faster. So I think I think people are spoiled. It's this thing we call Moore's Law, which means that transistors have gotten smaller, but it also has really corresponded to computers getting faster. And it's hard, kind of trying to understand what it means for things to get exponentially faster. 50% improvement per year is a hard thing for people to grasp when you look out 10 years and say, oh, that means 1,000 times faster. What does that mean I could do with a computer if it were 1,000 times faster? scientists in computing are, have really looked at what are some of the kinds of problems they could solve with an exascale computer. But I think for the general public, it can be hard to imagine what we could do.
Okay, another question from the audience.
Kathy, when you were working on circulation in the heart, one of the products of your research was a visualization of the heart working. And I'm wondering if you could use that as an example and talk about what is it that a scientist can learn from a visualization that he or she can't learn from just looking at the data itself. For example, you talked a little bit about climate change maps, and you can actually see the hurricanes if you know when to look. But, and I know that John Bell, for example, has been doing visualizations of flames. And what is it that you can actually learn as a scientist from that visualization that you couldn't see by looking at the beating heart itself or at the flame itself?
You know, in both these cases, there are phenomena that are either so small or happen so fast that you really can't see them. So in something like the blood flow in the heart, there is, the valves actually get pushed shut by these vortices that form behind the heart valves. And I think this was not, entirely understood, but now with simulations, we're able to see exactly how this happens. And similarly in combustion, there are places where there are a higher density of emissions being generated because of the way the flame is structured and exactly what is happening in different parts of the flame. And so some of these things you may be able to see in a in a laboratory setting, but not those details. And so computers, simulations, and then visualizations can allow you to see things that are really not visible with experiments. So I like to think of supercomputers as helping us look at things that are too big, too small, too fast, or too slow to be looked at with a human eye. And so that's really where this comes up. And of course, we have incredibly powerful scientific instruments to try to look at things that are too small or too big, looking at the universe, or things that move very slowly, like climate change. But it is still the case that are things you can't capture with those measurement devices. And at the same time, scientific visualization itself, aside, there's the simulation problem, but visualization is very important because the data sets are so large, and the human eye is very good at taking in very complicated images and movies of things happening and noticing that there's some phenomenon over here like a hurricane, whereas if you were just looking at a set of numbers saying, here's the air velocity, would you detect that there was a hurricane in that set of numbers? Not necessarily, right? So you really need visualization because these data sets are so large. And so I think those are some of the kinds of examples.
So where is the world's fastest supercomputer right now?
World's fastest supercomputer is at Lawrence Livermore National Lab. It's a new system called Sequoia, and it is a 20 petaflop system. So.
Okay, any other questions from the audience?
Hi. Berkeley Lab is very applications-oriented, I think, among a lot of the national labs. I was wondering if you could say something about, and a lot of what you talked about in the division is applications-oriented, climate change or reducing energy use or whatever. What sorts of just kind of pure science-y things, which might have applications in the future, but what sorts of just pure science stuff is being done now, or would you like to see being done now?
Well, I think that in each of the science disciplines represented here at the lab, there are fundamental questions that can lead to applications in the future. Certainly in the materials area, understanding people are looking at fundamental materials for even things like computing devices, or I mentioned LED lighting. So the discovery about LED lighting, they were trying to understand why when you LED lights are very efficient, except if you try to use them at the scale that you might in a whole room or for very large areas or a building. And so what they found was there was a phenomenon called the Auger effect, and I'm not going to try to explain it here, but it had to do with exactly the way electrons go into this material and what happens when they get to combine. That is a fundamental understanding of materials and structures and the atomic structure that can then lead to an application later. And I think that really, what I think is really important about Berkeley Lab is the focus on the scientific foundations as well as really understanding the applications of some of those, and that it's very important that right now we're looking at problems in biology that might lead to in 10 or 20 years to new discoveries in health and understanding of disease, or that might lead to new biofuels, or or in other areas in climate change, really actually helping us understand how we could reverse things. So those are all, I think, some of the basic science areas. But it's also really important, as I said, as a scientist myself, I think it's really important to be able to explore things that are not necessarily going to work out or not necessarily going to have an impact. And it's really, as a laboratory that does a lot of fundamental science and across physics and chemistry and biology and all these different areas, that we don't know what some of those future applications will be. And it's really important that we have that foundational work that happens in understanding the basics of nuclei and so on, because we can, because it may lead to discoveries in the future.
So any other questions from the audience?
I have one.
Okay.
So here we are in 2012, and big news is this woman that was just hired to be the CEO of Yahoo is pregnant, and creating quite the shockwave that company was willing to do that. It's surprising that it's surprising, but I guess it isn't. But I was wondering about your career, and when you decided to go into this field. You don't have to say how many years ago, but I assume it's a predominantly male field. And how did you navigate that terrain? Was it an issue, or what they were saying in the news stories today? It's like if you have the skill, they don't really care so much. But I don't know what your take is on it.
It was the case that when I certainly as an undergraduate, I was normal. I was often the only female in a room of 20, 30 students, something like that. I mean, there are probably about 10%, 12, 15% women in computer science and undergraduate programs today, and the numbers go down a little bit when you get to, advanced, like master's and PhD level programs. And so, it is still, the numbers are low, and what that means is, statistically, you're likely to be in a room with only men if you're in a room with, 10 to 20 people or something like that. In general, though, it's a very young field, and I think that the men in it have been, in my experience, have been very supportive. And as you also said, in a science area, people do respect you for your ideas and your intelligence and your ability, your creativity and your ability to solve problems. And I think that is actually very, it's very attractive that as a woman and who's in a room full of men, that if you know what you're doing and you're good at it, then I think that generally I've felt like I've been very well supported. I do have 2 children. They're a little older. They're teenagers, but throughout my career, I've gone through the period of being pregnant and having young children at home and things like that. It is a constant balancing act. Yesterday, my husband was on a plane in one direction, and I was on a plane in the other direction coming home. And I have to say it's a little nerve-wracking to make sure that one of us is, always gets here by the end of the day. But it's, well, we'd have to ask my kids how they feel about it. But I think in general that, they kind of like the idea that their mom is a scientist too.
So with that, we've reached the end of the program. Thank you, Kathy. Thank you, audience. Please. We'll be back here on August 1st with the director of the LIGHT program and the Globally Transformative Technologies, Shashi Bulaswar. So I look forward to see you then. Thanks.